Hello everyone, and welcome to our sixth episode of the Advanced Zenoh tutorial. So while preparing this last episode, I was going through all the material that we have covered, and actually, I also had the chance through the weekend and toward the tail of last week to discuss again some aspect of Zenoh reliability, which I'll again hopefully clarify today, and so that way, those of you that had those questions will have a little bit more articulated answer, and those of you that didn't have it yet, you'll get the answer anyway. But before we get started with the new episode, I would like real quickly to make a quick time capsule and see actually what we went through in a way. Okay, because I think it's a good exercise to try to recall what we went through and the kind of material that we covered, so that in case you missed some episode, you can decide to go back and either look at the slides or perhaps or perhaps just listen the recording. I'm gonna change visualization. Maybe this makes it a little bit too busy, so let's get back to this view here. So if we look at the first part, right, the first part, but maybe actually I'll do like this. In the first part, right, that was the first episode, we introduced the basics of Zenoh, right, the structure of the stack, so the fact that Zenoh can run at the data link, the two protocol implementation of Zenoh, one in Rust, one in C, that being Zenoh Pico and targeting microcontroller, but making sure that both of them supports the full set of abstraction of the Zenoh protocol. We discussed topology, so the fact that you don't have any specific topological restriction in Zenoh, and we explained links. This is something that often is not fully appreciated the first time you get to meet Zenoh, because usually protocols that you find on the market don't support multiple links at the same time. But as we discussed in the first episode, you can actually have the same application running at the same time over serial, over Bluetooth, and perhaps over a quick or why not TCP/IP. Then we went and we covered all the programming abstraction, so PubSub, querybles, and explained how querybles and subscriber can be used actually to abstract storages, while a queryable is just a source, an oracle on the network that answer queries, and then that can be used either to represent something that reads out of a store, so the reading out of a database, or to represent distributed computations. We went through trying to explain completeness. This is something that not all of you will have to deal all the time, or perhaps never when using Zenoh, but we still discussed that. We discussed the Zenoh feature, so I listed all the features that are available in Zenoh, how you can enable or disable those, and we discussed all the different supported links, okay? I showed how you can configure links, right? Because if I want to listen on serial, on Unix socket, pipes, and quick, how do I do that? Well, we discussed how to do that. And then I went on discussing reliability. Well, we'll discuss again reliability because based on some of the questions that I've had on Discord, and as I said, I was answering last weekend and perhaps Friday, I think we need to do a deep dive. There are some other mechanisms that you need to understand. We discussed storage alignment. So in Zenoh, we have the ability of aligning storage. As of today, only traditional storage, not time series. Time series is something we'll do probably going forward. And again, the nice things of our storage alignment algorithm is that, in fact, if you build a new plugin, say for your favorite database, that will leverage the storage alignment framework that we have designed. Then we discussed some aspect about Rust API and how you should configure plugin to make sure that the loading doesn't fail, let's say silently, just by logging a warning, but actually you stop loading the plugin if you are unable to load it because of API incompatibility. Recall in Rust there is no API stability. Then we discussed time and ordering in Zenoh. We discussed the delete. We discussed liveness token and how this is a very useful mechanism to do group management. Okay, so you can do group management in a very flexible manner, and you do that by liveness token. Then we discussed the fact that you can declare liveness token, you can subscribe, you can query those. We covered then connectivity information. And there were some questions on Discord this weekend asking, how do I know when a new session is established, and so on and so forth. Well, you can get all of those information out of connectivity information, and we discussed that on the webinar, as well as the matching status, right? How do I know if I'm matching something or not? Something else that we added recently in the last release of Zenoh was QoS remapping. This is something quite powerful because allows you at deployment time to decide when crossing a certain boundary if you want to remap or change QoS for certain keys. And again, I will make some more reference to this feature probably today. Then part 4, we dive into scouting, okay? Because again, scouting is something that isn't always fully understood in Zenoh. So hopefully the 4th episode provided through some animation and example, a little bit more insights on how scouting works. We discussed the default behavior. We discussed how gossip scouting works, and the fact that you can actually mix and match these in different portions of your system. Then we discussed discovery, right? Because scouting is about finding out who is around. Discovery is about distributing declaration concerning subscription and queryable. So we discussed the key idea, we discussed how and under which cases information is distributed, we discussed the concept of aggregation, which is very powerful for scalability, and we discussed interest, which is a mechanism that allows you to decide whether or not, or to express whether or not you're interested in receiving these kind of declarations. And again, if you are a small microcontroller, perhaps you don't want to receive any declaration because in any case, you're going to publish whether or not your publisher is matching subscribers, okay? Then we went through routing algorithms. I explained that in Zenoh we have 2 routing algorithms, right? Peer-to-peer and link state. I explained how to configure routing. I showed the fact that you can retrieve from any node a view of the routing graph that node has. Actually, this view is eventually consistent. And in that webinar, if you look at the recording, I was showing how quickly this view converge. Then in part 5th, which was one of my favorite webinar, we did interceptors, access control, but more importantly, we went through shared memory. So we went through shared memory in Zenoh, explained, how shared memory works, the fact that we have this concept of provider, where the default provider is POSIX shared memory, but you can implement your own provider to plug, let's say, a GPU or some custom hardware, or sometimes when you have a system on chip between the microcontroller and the microprocessor, you have shared memory. And so that shared memory could become a custom provider too. We looked at how you can transparently use our shared memory buffer on regular Zenoh operation, whether those are put, whether those are reply, okay, and how you can transparently consume those. I showed how I changed the Zcam example, which is one of the demo out of the Zenoh demo repository on GitHub, the Eclipse Zenoh GitHub page, that does video streaming. And I showed you how easy it is to use share memory for sending video when communicating on the same host. And then transparently, if you had a subscriber for the video across the network, Zenoh will transparently then make sure that the actual data is sent as opposed to just emit information for the buffer. And then I answered finally a question, right, that I'd always said in previous webinars, in previous year, actually, you could do this, but I never showed you how, okay? And what was this, you could do this? So some people in certain application domain, right, require polling and require polling for various reasons. First, because they need nanosecond level latency. Okay, they don't want to cross kernel when communicating, and it has to be absolute shared memory. Actually, you can do that very easily with Zenoh shared memory, and actually using a combination of Zenoh primitive and Zenoh shared memory. And in the fifth episode, I actually showed how you can create polling producer consumer over shared memory one to one, a polling producer, single producer and consumer, and then using Futex, I also showed, if you're running on Linux, how you can do a one-to-N that is not polling, but you just are triggered when there is information available. And using this mechanism, you can have, latency that are in the order of, you measure them in nanoseconds as opposed to microseconds, okay? Whether, depending on your hardware, could be tens or hundreds of microseconds, as opposed to tens or few microseconds. Now, we are not done. For those of you that attended that webinar, you noticed that there was some unsafe code. More importantly, when we had to essentially cast the shared memory buffer into the shared data that we're using to coordinate in order to implement this abstraction. Obviously, we are working, and there is already a pull request ready to be merged to ensure that you can have a completely type-safe abstraction to do this kind of to build this kind of applications, or in fact communication mechanism, so that you don't have to do any unsafe code, which is, I think, good. Okay, so that was a lot, because only that, was 220 slides. And so let's now officially, after this recap of previous episodes, let's move to the menu of the day. Okay, as I mentioned, I want to go back reliability. So we covered reliability, but I feel, based on the question that I see on our Discord channel, that there are some fundamental aspects of reliability that are sometimes underestimated. And so I want to start with some very important theoretical results, which, if you're not familiar with those, are hard to believe, but they are actually, very important theoretical results in our domain. And the first reflection I want to do is on reliability, progress, and memory. So theoretically, it has been proven, actually in the 80s, I think it was 85, that reliable communication requires either to give up progress or to assume that you have infinite amount of memory. And here I mean reliable communication on a synchronous system. Notice that the network we use in 99.9% of our systems, right, are asynchronous networks. So why so? The main reason, just to give you an intuition, is that in an asynchronous system, think about the internet, right? It's very hard for me to tell if a process has crashed or it is extremely slow. And in fact, I can't really tell. And so if I'm trying to communicate, even in a very simple case, right, to application across an asynchronous network, since I cannot tell if it's behaving as being very slow or perhaps is just crashed or whatever, okay, it has failed, then the point is either I have to give up progress, okay, because maybe it crashed and is restarting, and if I send data, it won't receive, so I have no reliability. Or else, if I don't want to give up progress, I don't know how much memory I will need to store the information I'm producing that I would eventually want this other application to receive. And so this is the intuition of the problem that leads to this theoretical impossibility that in a synchronous system, if you want reliable communication, you either assume you have infinite amount of memory, which obviously we don't have, or you give up progress. But then you come into the real world, right? When we are engineers, we need to build system, and you say, but I mean, actually, I can't give up progress either, right? But if you can't give up progress, that means you give up reliability. But sometimes you say, yeah, but I can't give up reliability either. Yeah, but well, know that there is an impossibility result. So what we do in Zenoh, we give you mechanism to help you deal with this impossibility result. But you need to, first of all, realize, digest that this is like the elephant in the room that we need to deal with. And the more your system is open and asymmetric, the more you'll struggle with this kind, and we struggle with this kind of problems. Okay, now, as I emphasized open system, the other things that you should realize that if you have an open system, reliability in open system means that, again, if you assume that you have limited memory, okay, because you can't do differently. So if we talk about open system, again, in an open system, you can't assume unlimited amount of memory. And at the same time, right, there are very little assumption you can make about the application you will be dealing with if it's an open system. But then if you need to have reliable communication, the implication is that the pace at which you'll be able to produce data will be decided by the slowest application. Now, the question is that really what you want in your system, right? Just for you to realize, right? Suppose I'm sending, let's make an example with a price update once every second, okay? It is sufficient that somewhere in the network, right? And I'm just not talking about Zen, I'm talking in general, that in the network there is someone that reads 1 per hour, right? That eventually my buffer will fill up, and eventually, right, I will be able to produce 1 per hour. Is that what you want? No. Those are the challenges of open systems. And this is why you always have to keep in mind that reliability, right, how we typically think about it, because we typically think of reliability, I produce something, everyone gets it unless they've crashed, right? But then there is the temporal aspect and there is the progress. Okay, so with this background in mind, let's now take a look and a deeper look into Zenoh reliability, and let's see how you should deal with reliability, with progress, with memory in open systems, and what are the mechanisms that Zenoh provides you. Okay, so first of all, as we discussed in previous episodes, in general, in Zenoh, right, if you have a publisher and a subscriber, this publisher and subscriber might talk through a network of, let's say Zenoh routers, could actually be other Zenoh peers, but let's say a network of Zenoh routers. This is the most general case. Or they could talk peer to peer. That case, it's easier. It's let's say a trivialized case compared to this. Now, in Zenoh, first of all, in order to do reliable communication, you should make sure that you have at least one reliable link configured. Okay, and by default, the data that you publish in Zenoh is reliable, but as we'll see, it has drop congestion control mode, and we'll get to that in a moment. Okay. Now, the default reliability in Zenoh is hop to hop, which means that if this publisher is producing data and sending, and that subscriber is one of the subscriber, right? Zenoh will, by default, will ensure reliability, right? Assuming that end-to-end reliability exists, right? Because of hop-to-hop reliability, right? Now, this works if there are no crashes in your routing networks. And the nice feature of hop-to-hop reliability is that is very, very scalable, right? In this kind of network, the publisher A, which might be a microcontroller, could have a zillion of subscribers, right, across the globe, but still it only has a reliability session with the next hop, which is B. So in terms of reliability state, that's very, very compact, okay? So that's very good for scalability. Then obviously what might happen if there is a crash in the routing network, right? Then Zenoh reroute the data, but as a consequence, right, what might happen is that some of the message might not be received by the um, by the subscriber. Okay, why? Because, well, perhaps the router D crashed after he had received some message that had been acknowledged to C and before he could forward to E. Okay, so in that case, those messages would be lost. Okay, so if we look at reliability, so reliability can be controlled on a per sample manner when you do a put operation on a session. So here, for instance, I have a session Z. I do Z put, daily quote in Brazilian, União faz a força. Okay, and I say reliability is reliable. You have two kinds of reliability: reliable and best effort. Or you can configure it when creating a publisher. So you see that here I declare a publisher for the key daily quote in Latin, and I say reliability reliable. And again, if I don't specify, as we will see, congestion control, the default will be dropped as we see in this slide. So as per reliability, I can control the congestion control per sample, okay? So in this case, I can do zput, daily quote Latin, per aspera ad astra, and the default congestion control is drop. In this case, I want this to be block, and I set it block, and I can set it also by the creation of the publisher. We'll see with some animation, or let's try really to understand what is the difference between block and drop. Okay. So let's start with reliability. So reliable reliability plus congestion control drop. So the congestion control drop uses an heuristic to decide whether a fragment, and in fact, actually, it's a batch. But let's forget about batch. I want to keep things a little bit more simple. So I want to give you the intuition, and then at the end of once I give you the intuition, I'll tell you where I took some poetic licenses. Okay. But again, so the point is that whenever you have data, right, your data could be just one fragment or might need it to be fragmented. But the point is, we have some heuristic to decide whether the given fragment, and in fact the given batch you're trying to send, will be queued or dropped. And why do we do that? Because these help us in ensuring that when we detect congestion, then and that Zenoh queues are full, as opposed to accumulate additional load, right? We do load shedding, avoid piling up stale data, and that ensures that when the network congestion is over, right, the communication will resume as it was. On the other side, right, if you're trying to write more data that can get through the network, because imagine I'm communicating through a wireless area network where I get, at best 10 megabit per second, and you're sending, I don't know, 100 megabit per second. You can get through 100 megabit per second. You can get through 10 megabit per second, right? There is no magic. So what does that mean? That means that either, right, you will lower the rate of transmission at 10 megabit per second, which means you will eventually have to block your application and write data at the pace of 10 megabit per second. That's option one, right? Because otherwise you run out of memory. The other option is, well, I don't want to slow down, right? Maybe that's some periodic data. Then you have to drop. And so it's like a natural downsampling of what will happen. Okay, so um, going next to give you the intuition, let's assume that we do a put operation. Okay, by default, this will be reliable with congestion control drop. And this is the case we are investigating. Let's assume that this is some fairly sizable chunk of data that results in 3 fragment. Okay, so this happens when what you try to send is bigger than a batch. So we have 3 batches that we want to send. And then next, what Zenoh will, after Zenoh does this, it will try to push this batch into the transmission queue. Okay? And by the way, the length of this queue is configurable, but by default, you have 2 slots. And in parallel, there is a task, which is the TX task. We'll discuss that in a little bit, that does nothing else, right? But essentially takes things out of the transmission queue and send them on the network, okay? So Let's assume again now that we have reliable congestion control block and the queue is empty. So in this case, right, we have three fragments. Two fragments are pushed into the sending queue, and now your put is blocked, right? Why? Because there is one more fragment I need to send, but there is no, I cannot put it anywhere, right? So in this case, what happens is that you will be blocked. Once a fragment is sent, one slot is freed, you'll be able to put to enqueue the second fragment, and the put operation will return. Okay? So this is if you are using block congestion control. So put with reliable and block. Now, what if the queue is full? Well, if the queue is full, then when using block congestion control, I mean, there are no resources available. So the only things we can do is to prevent progress. So your put operation will block, okay? And will block until obviously there is some space made to enqueue all those fragments, as we saw before. Okay, now let's look at the reliable plus congestion control drop. And here things get a little bit more interesting, okay? So if we look at this case, then I do have still a sample that takes, fairly big, that requires 3 batches to be sent. I have only 2 batches slot available, right? I put the 2 batch, and then what do I do? Okay, because again, if the network is congested, very badly congested, depending on the network and depending what I'm trying to send, this could take quite some time. Okay, and this would block the transmission of everything else on that specific priority. And this is not something we want to do because, as we said, for some application, we cannot afford to block the progress. And if you're running on a link like TCP/IP, you will be completely stuck, which is not something that many applications can afford. So in this case, when you're using the default congestion control that is blocked, we have an heuristics. We look at how long time we wait to enqueue this batch. And then in the first case is if a slot is freed, okay, and in the transmission queue before the timeout expires, then we enqueue the fragment, okay? But again, if you think about this picture, right, if we go back here, you have to realize that this exercise, if you are on a routed network, will happen at every routing point. So sometimes I get the request, or we get the request, can I know where something is dropped? Well, the answer is actually no, because it would be too much bookkeeping, right? I might be sending something here, but the network might be congested between D and E. And so I might be dropping something here, right? So you just need to understand that if you have something that is marked as reliable, but congestion control drop, we might still drop it if we detect congestion. And there is a full heuristic to decide when to do that. So let's go back to the animation. We were at case A. Okay, here we are. Okay, so if a slot here gets freed before this timer expires, good, we get to send it, okay? And by the way, the heuristic that we have in Zenoh obviously takes into account the fact that the more I've sent, the more it makes sense to wait up to a certain limit, okay? And if I've not sent anything yet, right? So if in fact it's the first fragment of a data payload that I'm trying to send, and there is no space, then we might drop a little bit more aggressively. Okay. Otherwise, in the case B, if the dropping timeout expires, then the frame that contains this fragment, and if the full frame is just this fragment, is dropped. Okay. And as a consequence, on the other side, the data won't be received. Okay, so this is how congestion control drop works. I mean, in a way, right, um, it helps emulating what happens to some extent, and while making it easier to configure the behavior, what would happen if you were to use UDP, okay, to some extent. Because if you think, if you are usually on non-aerospatial application, most of the losses that happens on when communicating on UDP, they are due to buffer being full, either on the sending, on the receiving, or in the middle, right, in some router. So this is a similar mechanism with some additional control. Okay. Now let's look at priority now. Now in Zenoh we have several different level of priorities, and every priority has a different queue. Okay. Um, Higher priority samples always overtake lower priority ones. And as I explained in the previous episodes, actually, you can configure a link and dedicate them to a given priority or a given priority range. Okay. You can control priority for each individual put. So you will have a Z put priority, and in this case, priority high for this quote, Kumanja Famudiki. Or you can define a priority when declaring a publisher. The default priority is data, which is 5. Okay. Now the question is, okay, I'm sending some large data. So let me give an example. There are some people sending, big LiDAR images um, at a rate that kind of saturate the Wi-Fi network. If you're sending other data, what might happen? Well, what will happen is that eventually, right, there will be some saturation of the network. We will drop some samples. So that's the kind of downsampling that you want. Okay. But if you cannot afford to send to do any downsampling, then what you should do, okay, is to accept to send this data as background. So if you're sending large data, one approach is that you write it with a priority background, okay, so it doesn't stop anything else, right? And you use congestion control block. In the next release, of Zenoh, which will be, we'll start doing at the tail of this week, so will be available early next week. We're introducing yet another congestion control mode to really facilitate dealing with sending very large data and kind of doing automatically this kind of priority declaration. Okay, but this you can do in a way kind of by hand. Okay. Okay, so moving forward, how do you configure the queue? You can configure the size of the queue per priority, and we will look at configuration at the tail of this webinar. But in general, out of the shelf, you have 2 slots for each priority level. Notice that increasing the queue is good for throughput, right? But has an impact on latency, and obviously has an impact on memory utilization too. So there is, as always, a balance between throughput and latency, and you can decide, how you want to play that balance. Okay, as we've discussed reliability, we have lots of Zenoh users that always run only on TCP/IP. Why? Because on many networks, UDP isn't even open or allowed. And so again, the congestion control drop is quite important to emulate downsampling when the network get congested, and to be, let's say, reliable otherwise. You can also, and so when running on TCP/IP, there is a very thin difference between best effort and reliable with congestion control block. If you run on UDP, or if you enable a UDP endpoint, right, and you can do just by, well, in fact, I could show it here. If you also want to enable UDP, it is as simple as doing like this. Okay, so if you also enable a UDP link, then in this case, whenever you send data in a best effort manner, that will go through the UDP transport, a link. Okay, so we've discussed hop-to-hop reliability. We've discussed how congestion control is done in Zenoh. As I mentioned, there is a third way of congestion control that we are going to release next week, and I'll probably explain it in a separate webinar in September. What if you really want to have end-to-end reliability? Okay, because even if you use congestion control block, right? If we go back here for a moment on this one, even if I'm using reliable channels and congestion control block, right? If this crashes, I might still use messages end-to-end. Why? Because that's a routed communication. If you are communicating peer-to-peer, you don't have that problem. But as soon as you scale out and you're communicating over a graph, then that problem exists. And if that is a problem for your application, obviously there is a solution in Zenoh. And what is the solution? We'll get to that in a moment. Okay, that's end-to-end reliability. So suppose again that we want to guarantee end-to-end reliability in spite of failures in the routing path. In that case, we have something called advanced publish subscribe. And again, we are discussing internally whether some of this feature will be pushed at the core of Zenoh, but right now it's built on top of Zenoh and will remain there for at least for the few months to come. But the basic idea here is that the publisher keeps a local cache that can be queried by the subscriber when missing samples are detected. And again, here I'm showing you the simple story because this cache actually could be kept throughout the routing path. But let's keep the simple case in which we're keeping the cache only at the source. Okay. So in this case, suppose I have a publisher that produce some data. The publisher has a publisher ID. The sequence number is 18, and it's a given key value. So this is routed and is received by the subscriber, but it's kept in the cache. Then it publishes a new value that's still received. Then it publishes the key value with sequence number 20. And what happens is that while it was being routed by B, it crashes. So what happens is that the subscriber never receives it. Then the publisher yet another key value, in this case with sequence number 21. And when this is received by the subscriber will say, hey, hold on a moment, I've not received 20. So a gap will be detected, and it will try to recover it by means of a query on the publisher cache. So it will literally do a Zenoh get under the hood on the sample with sequence number 20, okay? And that will be obviously sent back so that at this point, the actual subscriber can deliver the sample in the right order, okay, and without any losses. So the advanced PubSub provides you with the ability to configure heartbeat or a periodic query for the last sample missed. You should use ideally heartbeat, but it depends on whether you have more publisher than subscriber and so on and so forth. And by default, this cache keeps the last key value that were put. And again, anything that is out of this will be out of history. Why there are this key value? Again, because we don't want to block, we cannot afford infinite amount of memory. If you want to have a blocking behavior, that could be configurable. But again, in this the kind of system we build, think twice if you are accepting to block because of someone misbehaving. Okay, because then all of a sudden, when a distributed system, as Leslie Lamport used to quote, right, the distributed system is a system where everything stopped working because of the crash of a machine you've never heard of before. So to paraphrase this, you always have to be careful on the adversarial argument. And that could be malicious attack, could be just a bug, right? But assuming and accepting that your application will stop progressing if something starts misbehaving makes you build a very fragile system. So I think that's an assumption as much as possible that should be avoided. In terms of API, if you want to use the advanced publish subscriber, then you just have to tap into the Zenoh X crate. That's where we put the extension of Zenoh, built on top of Zenoh. And then this is how essentially you configure or create a publisher, right? You declare a publisher, you configure a cache with a max history, And in this case, I use the sample misdetection heartbeat in this specific example. And likewise for the advanced subscriber, okay? Now, one topic I want to cover, which moves us already into the topic of configuration, are executors. Because I don't know how many of you know that this can be controlled in Zenoh, but you can, okay? So, but before understanding how we can control threading, let's try to understand how executors are organized in Zenoh. Conceptually in Zenoh, and again, that's logically, we have 5 executors. There is a logical executor that takes care of the receiving task. So anything that is received by runtime, there is a logical executor. There is an executor for dealing with the sending task. There is an executor dedicated to accepting new session. Why that? Because, by the way, if you are in applications that are throughput intensive, you can do the test, right? And probably you have experience with other technology. If I'm busy sending and receiving data, I might never accept, or very not. I might start connection acceptance. Okay, dedicating an executor makes sure that that never happens. Then we have another executor that is dedicated to routing activity, and then yet another executor for application tasks. And again, here we are talking about Tokyo executors. Okay. Now, do you really need 5 physical executor? Well, the answer is no. Okay, the actual Tokyo executor can be shared among different functions, and not only can be shared, but then you can decide how many worker threads and how many blocking threads each of these executor will have. So here you have an example of one of the minimal configuration you can use with Zenoh, where essentially you hand over the Rx, the acceptor, and the net to the application. You define the application executor with 2 worker threads and 1 blocking threads, and the TX 1 thread, worker thread, and 1 thread for blocking task. Okay, so you need to define this environment variable before running your application, and then you will see that as opposed to depending on your machine, as opposed to having the Tokyo default, which will do 1 physical thread per core, you will see that in this case you will have only 5 threads. Okay, good. Now let's move to configuration. And I think the best way to discuss configuration is actually to go through the configuration file that is in Zenoh. Because whenever you want to know if something is configurable or how it is configurable, there is this default config.json. Maybe I can also show it here. GitHub Eclipse. So it's exactly the same file here, okay? And any new feature that we add, there is always a good documentation. So let's go top to bottom and let's review the configuration of Zenoh. So let me actually remove all the things that are unneeded so we can gain a little bit in real estate. Okay, so let's start with the mode. So in Zenoh, an application can run as a peer or a client. And then, as you know, we also have routers. That's the famous Zenoh, right? And so in the configuration, you can define the mode of the application. And there are certain parameters, configuration parameters, that are mode dependent, as we will see. You can define some metadata. In this metadata, you can put whatever you want, okay? Literally, whatever you want. And this will be retrievable through the admin space if you enable the admin space. So it's a good way of piggybacking whatever information makes sense to add additional information about your application. Then we have the connect session. And the connect, this is essentially, if you want to define some endpoints, okay, you can define here the list of endpoints to which you might want to connect. And again, I gave example in the webinar on how to do that for Unix pipes, Unix sockets, and so on and so forth. Yeah, I mean, those are some advanced configuration. I'll let you read the doc. Then there is the listen. I mean, likewise, in this case, it's a mode dependent configuration. You can define, in the same configuration file, the endpoints, if in case you're a router or in case you are a peer. Okay, so you see that usually router listen on a 7447, while a peer listens on an ephemeral port. Okay, and then you can decide again various timeout in terms of next try when connecting and so on and so forth. This is a little bit more interesting configuration. So when you do a Zenoh open, then the question is when should the open return? Okay, and by default is that it will return once you have established a session with anything that you've scouted, if scouting is enabled. Okay, and after you have sent the declares. If you set to false, then you won't wait for declare to be sent. Okay. Then you have discussed, and by the way, declare we have discussed in the Zenoh webinar, I think episode probably 4. Yeah, episode 4. Then you have scouting. And already you can decide whether or not you want to enable multicast scouting. What is the address you're going to use for multicast scouting? Over which interface, right? You might want to specify the interface. What is the time to leave? The auto connect. So you see that, for instance, a router, even if you enable scouting, they won't auto connect to anybody. Peers will auto connect to router and peers, and by default, client will only auto connect to router. And if you want client to auto connect also to peers, you could do like this, right? But that's not the, well, peer as opposed to peer. But this is not the default configuration. Okay, the default configuration is just as I showed. Then, yeah, this is the auto connect strategy we discussed. And then we have gossip routing, gossip scouting, which is enabled by default, won't do multi-hop. And again, you have the ability to control whether you auto connect or not. Okay. Timestamping. You can decide whether timestamping is enabled or not. By default, timestamping is enabled only on routers. Why? Because in general, we assume that routers are on a trusted portion of the infrastructure. And especially if you're using storages, once you hit a router, your message will be timestamped. And that way we have total ordering in the system. But you can enable timestamp also on peers and client. Again, we discussed times and Zenoh, I believe, still in episode 3 or 4. Okay, I mean, this I think we can skip. This is the time to wait for incoming interest. And if we skip down, I don't want to cover namespace. There is some configuration about transport, so you can decide whether or not you want to enable the low latency transport. I briefly touched on this when we discussed the different kind of transport that we supported. You can decide whether or not you want to enable transparent compression from here. And again, this multicast, so Zenoh can also communicate through multicast. And this is the configuration when using the UDP multicast transport as opposed to unicast or TCP/IP. Now, this one is interesting because you have the TX, okay? You can control here the sequence number resolution. Again, if you're running on a constrained network, you want to reduce it to 8-bit, for instance. The lease you can control by default is a 10-second. And in this 10-second, we expect to receive at least 3 heartbeat to consider you alive. You can control the batch size, okay? And recall the number of slot in the queue, all the batch size, okay? So each time you're adding a slot, essentially you are taking 64 kilobyte of RAM. Then congestion control. So in the drop, okay, there is a wait before drop. So in microseconds, how much we wait before dropping a fragment, okay, and the maximum time we might wait, right, for message that include multiple fragments. And then if we are using congestion control block, the problem is, as I mentioned before, that might be an application that is unresponsive, right? So what do? Do we block all the system? We can't afford that. So at some point, we will kick this application out and we'll close a session. And here you can control after how long time this session will be closed. Then batching, automatic batching is enabled by default. You can disable it if you want. And then there is how we allocate batches on the queue. So if you're not using a given priority, right? So if I go back, so you see we have 7 priorities, and in this case, 2 slots per priority, which means to batch. But suppose your application is using only default priority, which is data. Would be stupid to allocate buffer for everything else. So that, well, it depends then on the kind of application. But in this case, wouldn't be great to do that. So what you could do is that you could, in that case, just allocate lazily, so that only the buffer that you're using will actually be allocated. Okay. Let's see. Yeah. So share memory is now enabled by default. And again, we covered it in the previous webinar. And this is the authentication plugin. So if you want to use user ID authentication, then you can just configure this or configure the public and private keys here. Admin space is not enabled by default, so you have to enable it by setting this true. And then you can control the read-write access. So by default, you cannot write the admin space for security reason. But if you want to be able to write it, because that has consequences on the configuration of your runtime, you can set this to true. And then there is the part on plugins, which actually we've already covered in previous webinar, so I won't go through it. And that is it. So let me go back to the slides. So we've covered the bulk of configuration 2. And so now it's time for our series epilogue. So it actually was, quite some work to put together this 6 series episode. I mean, it was supposed to be 3 series episode. Then collectively we decided to extend it to 6. But honestly, it was fun. I hope you can tell that I enjoy a lot doing this webinar. I hope that you enjoy the content and that you find it insightful. And I've started actually putting together a Creative Commons book that covers the content of this webinar. So not sure if I'll manage to complete it over the summer, but this will be my let's say second half of the year project. So I want to have a little booklet that actually puts down all of the things that we have discussed in this webinar, perhaps a little bit more, have it on Creative Commons so we can collectively make it even better, and make it sure that everyone else can learn even more quickly Zenoh, get up to speed, and have fun building great distributed systems. And with that, at least in Europe, in Southern Europe, August is the time for summer break. So for those of you that are going on summer break, enjoy, relax, recharge batteries. And for those of you that are maybe a little bit more from Northern Europe or other country and have already had their break, then you had a very great break. And in any case, we'll resume our series in September. So I look forward to seeing you back then. So enjoy your summer. And what we're going to do now is to check if there are questions and make sure that we answer those. So let me go back to Restream. Oh, okay. So by the way, thank you, AG. This is the 100th video today. I didn't know that. So that's nice. Nice celebration. Thank you for letting me know. Concerning your question on trust zones, can you articulate? Okay, and then Nikolai, the question concerning prioritization. I hope I answered the question. So if you're using different priorities for the various put, right, they won't conflict for the same resources. And that's independent of whether or not you have separate links, just to be clear. So let me go back. Okay. Okay, let me go back here for a moment. Yeah. So there are different queues, whether or not these queues are then mapping to different links. So if we take the example of TCP/IP, on theory, I could have one TCP/IP connection per priority with a Zenoh queue behind. Okay, but that's not required. Even if there is a single TCP/IP connection, we still have multiple queues, right? And then we will do priority preemption when sending on this TCP/IP connection. And what you pay in terms of head-of-line blocking, if we go back a little bit, is just the time to send a batch or a fragment. Okay, and this is something I'd covered in the past. I should have slides, I believe, here somewhere. Let me check. Okay, actually, I didn't put the animation in these slides. Oh, no, but I've covered it in the past. So actually, I can find that real quick. So give me 30 seconds. I'll pull out the deck that does the animation that I wanted to share to make this quite visual. Yeah, here we go. This is precisely what I wanted. So I've presented this slide in the past. Up. Okay, so essentially, right, even if you have a single link, imagine this is a TCP/IP connection. If I'm writing data from different priorities, okay, suppose that I write something at priority n, priorities n+1, priority n+2. This is logical priority, okay? Then in this case, what will happen, okay, is that suppose this is like a LiDAR image, 10 megabyte, whatever. This is something that is still pretty big, and this is a control message. Okay, I want this to preempt anything else. So even if I'm using a single link, okay, what will happen is that I end up writing the first fragment for this big chunk of data. Then this will be preempted as soon as someone does the put for the priority n+1, and will start writing the fragment n+1. Okay, and then at this point, as soon as I write this, okay, once the sending is completed, I'll start sending the fragment for priority n+2, which contained the entire data, and then resume in priority order. Okay, so indeed, if something is blocked at priority n, doesn't mean it's blocked at priority n+1, and that you have the preemption. And this is also the reason why I was saying, if you really need to send, I mean, there was a post from this guy sending 600 megabyte file over Zenoh, right? Then in that case, put it background and blocking. Okay, that's probably the best way of dealing with that kind of size. Okay, so let me go back to Q&A. So, Eji, I still let me know if you have a follow-up question on trust zones. But I mean, on trust zones, we don't have anything specific today. Okay. Okay. There are more questions. We are actually 1 minute beyond the allocated time. So thank you everyone for joining. Once again, have a great summer, and I'll see you in September. Ciao.